Hey guys, this is Sig from Melda.io, and I'm back again with more Golang tutorials for you. I had a request to do a video about concurrency in Golang, specifically things like GoRoutines, channels, Mutexes, general multi-threaded programming in Go. And so I figured that would be a thumbnail video to do. So what I want to do is give you a practical example of how you can write concurrent programs in Go and tell you a little bit about some of the pitfalls and some of the things you might run into. So for this example, I compared a little API that will get a hit, and I found this Exchange API on GitHub. I'll put a link to it in the description below. It's a fun little project. It's basically, I think, a daily kind of API endpoint upload. And what it does is it allows you to fetch currencies, so the world's currencies, current sort of real money and cryptocurrencies, if that's your thing. And it just gives you a list of them. And then for each currency, you can use this in your code to go in and fetch the rate that the currency has in relation to all the other currencies. So you could write a low currency exchange using this API. So that's what we're going to do today. And then we'll show you some things of how we can make it concurrent. So if we go into our editor here, I'll just walk you through. So I've implemented some base stuff for us to get started because we want to focus on concurrency, not on the business logic here. So what I've done is I've written this little currency exchange. So my currency exchange is a struct, and it has a map of string to currencies. So it has a bunch of currencies, like we just saw. And then for each currency, the currency has a unique code, like we just saw in the API as well. It has a name and it has some rates. And the rates are basically this currency's exchange rates relative to the code of the other currencies that the exchange rate pertains to. So basically what we just saw in the API. And then I have two functions in here. Fetch all currencies, which just hits that currency's endpoint and populates the currency's map. And then you can fetch currency rates. You basically give it a currency code, and then it goes out and fetches the currency rates. Right, so hitting that other API endpoint that we just saw to fetch a bunch of rates for each currency. And so our goal is to populate the currency exchange to have all the currencies and for each currency, all the rates to the other currencies in our currency exchange. So let's have a look at how we can do that. So I've actually written a little bit of boilerplate code to get us started. So I've got here a pretty naive implementation that just instantiates a new currency exchange, creates the currencies map, and then it calls fetch for all currencies that we just saw. Now, I've limited this to just fetch 10 because I don't want to fetch all of them for this demo. We don't want to overload the API. I'm just fetching 10 at a time. And then it actually goes through. So once it's fetched those, it goes through it and loops through all the currencies. And for each currency, it calls fetch currency rates, right? And then it goes in and it stores the rates for each currency. And then at the bottom here, it takes a benchmark of how long that took. And at the bottom, it prints out the results. So we can actually run this. Let's have a look and see what it looks like. So if we run this, there we go. So we got 10 currencies, and for each currency, we got 755 rates. And if we run it again, see what happens. Took a little bit longer there. We got some different currencies. You can see not all currencies have a name, but it works. When it kind of does what it means to do, it takes roughly around a second, and it fetches all these currencies. So now the question becomes, what if we wanted to speed this up a bit, right? How could we speed this up? Well, one thing you might say is, sure, we fetch all the currencies, but here we go through and we one by one fetch the rates for each currency. What if we were able to do that concurrently? What if we were able to do that in parallel, so to speak? Now, Go has several ways of implementing concurrency. By far the most simple implementation is using GoRoutines. So GoRoutines, if you look at here we go, GoRoutine anonymous function. It's basically, you create an anonymous function or a lambda function, and you say, run this as a Go routine. You use the Go keyword to say, Go func, and then do something. In this case, let's say we wanted to fetch the currency exchange rates concurrently. So we can create this concurrent function, and we'll pass it the code, and we can just stick all of this inside a concurrent function like this, right? So now what we're actually telling the Go compiler is when you reach this for loop, go for all the currencies and then spin up a Go routine, which is a separate thread, concurrent thread, and do this work that's inside this function inside the Go routine. So in here, we'll go and we'll make the API call, and we'll fetch the currency. And then, just like before, we should be able to print out the things at the end. So let's see if that works. I have a feeling we might run into some trouble. So this is kind of nonsense. We didn't get any rates. You see how quickly it finished. This is way too fast. And the problem is, of course, that now we're dealing in it with a concurrent program. So when we go out and we iterate through all these currencies and we say, do func, the basically go do this in a separate thread in a Go routine, the main thread, the one that's calling our application that our application is running in, doesn't wait for this to finish. The main thread just carries on. It prints it. It takes the end time. It prints things out, and then it exits down here. It doesn't care what's going on inside these Go func Go routines. It just carries on and does its thing, right? And so this is the problem we're running into. See, we were executing really quickly, so our Go routines haven't finished doing their work yet. Okay, so this is a common problem. So how can we solve this? Well, Go actually has a nice way of solving this, which is a concept called wait groups. So wait group are in the sync package, and we can go in and we can actually create a new wait group, like so. And a wait group, kind of like the name entails, is a variable that you can use to increase things to wait for and then decrease as things complete. And then you can basically assert that the wait group has fully completed. So if you think of it a little bit like a shared pointer or a reference pointer, it's called in some languages, it's basically just something that counts references. So you can increment it by X amount, and you can decrement it whenever things complete, and then you can wait for it to reach 0 again. So let's try doing that. So what we're waiting for to complete here is all our different Go routines, right? They're going out one by one. So what we need to do is we can do in here, and we can say for each time we iterate, let's add 1 to the wait group. So we're saying here's some work that we want to wait for. This is one entity of work going out and fetching the currency rates for one currency. So we can go ahead and we can add 1 and we can wait for this. So then what do we do at the end? We need to do a couple of things. First of all, inside our Go routine, we can now go in and say, I've done an entity of work, right? So our Go routine out here, this is outside of our Go routine. We say we add a bit of work to be done. And then inside the Go routine, we do the work, and then we say, great, the work's done. So the add keyword or function adds X amount of entities to do, and be done basically decrements 1 entity. So this is a common pattern that we use. And then our main favor we can do is we can simply call wait group, but wait. So what this will do is it will block the thread that's calling wait group that wait until the wait group reaches 0 again. So let's try this out now. So I'll clear this and run it again. Boom, and it works, right? So now we're getting full currency rate exchange again. And in fact, if we run this, you'll also notice that it's a lot faster than it was before. Before we were hitting around 800 milliseconds. Now we're doing all these API calls concurrently, so in parallel, although concurrent and parallel are a little bit different, but we're doing them concurrently. And so we've sped up our program by a lot, right? It's a lot faster now. However, there are also some problems of this. One of the problems that we have right now is that we have all these Go routines. They're going out and they're fetching stuff. That's fine. Then they go in here and they change, they mutate the map, which is our currency exchange. If we look at currency again, right? We have these two maps. We have a currencies map and we have a rates map. So our Go routines are changing the data inside these maps from different threads, potentially at the same time. Depending on how long this takes, you can imagine that multiple threads might start trying to write to this map at the same time. This is a real problem because Go maps by default are actually not read and write concurrent safe. Well, this is a terminology, right? Concurrent write safe or concurrent read safe. What that means is that a structure like a math in Golang will throw an exception if you try to read or write to it at the exact same time from different threads. And we can actually try this out. Let me just grab some code here, just to give you an example. So what we want to do now is we have this code. So let's go in and add a little bit of extra code. Here we go. Get rid of that. And so what we're doing now is we're spinning up another Go routine. Again, you can spin these up as many as you want, as many as your hardware can handle. And this Go routine, what it will do is it will go in and it will just keep hitting the currencies map and look if we've got any value for US dollar or for USD. So this is like a little extra loop that goes in, and it actually just keeps on, it does this forever. It just keeps on trying to read from our map and say, do you have anything for USD? Do you have anything for USD? If it does, great. Then it prints out USD. So let's try running this now. Clear, and we'll run. And now we get a whole bunch of exceptions. The whole thing is blown up, basically. Each of our GoRoutines is potentially firing an exception here. And this is because, again, we are accessing a shared resource from multiple threads at the same time. We've got a thread here in our GoRoutine trying to read from it. We've got multiple threads down here, one for each currency. We've got 10 currency thing fetched, so up to 10 threads at any given time trying to write to that at the same time. This is a really bad situation that we don't ever want to be in. So, how can we resolve this? Well, the easiest way to resolve this is using a so-called mutex. So what is a mutex? A mutex is essentially a data structure, but it acts as a sort of a pointer to a something that can only ever be acquired by one entity. So basically you can lock the mutex, and if you lock the mutex, then you are the only one who has ownership of it. And if you unlock the mutex, you leave it up for other people to grab as well. So think of it as a resource that can only be grabbed by one thread at a time. That's kind of where it comes in here. And Go has a great way of implementing this using, again, the sync package that we saw wait group from. And you can add to your struct something called sync.mutex. So this just adds a mutex to the My Currency Exchange struct. We could have named this mutex if we had multiple, but this just adds a base generic one to the struct. And now what we can do is, since Currency Exchange now has a sync.mutex field, whenever we access the shared resource from multiple threads, for example, down here, we can call lock. And when we're done accessing the resource, we can call unlock. Right? So now when we're writing, we're saying, when this Go routine comes in, it says, I'm about to change some shared state between multiple Go routines. That's a big no-no. I can't do that. I'm not allowed to do that unless I hold the mutex. So it goes in and it calls ce.lock. When it calls ce.lock, the operating system will basically figure out who has or who's in charge, who's next in line to pick up the mutex. So it will block, our Go routine will block and wait for the mutex to become available. So if another thread currently has the mutex and is changing the state, we can't, or this thread that we're coming from here cannot obtain the lock, cannot obtain the mutex lock. And so it sits there blocked, waiting for it to become its turn. And then eventually the other thing will unlock the mutex. We can then pick it up and do our work and so on and so forth. And this protects the shared resource from only ever being accessed by one thing at a time. So likewise, we can do the same thing up here, because this is another thing that we are accessing, a shared resource that we're accessing in a multi-threaded scenario. So now we've got mutex lock around both of our resource accessing. And now if we run it, we're back to things working just fine, right? So now we've got multiple threads sharing or mutating the state of a shared resource and doing so in a concurrent safe way, or in a thread safe way, it's also called. But there's one more thing I want to show you, because this is all good and well. This is a very well-established pattern. You can definitely use this. Using mutexes like this to protect resources is a great way of doing things. The thing is, so you can imagine, you kind of need one for each, unless you group things together, you kind of need one for each resource that you're trying to do. And so sometimes it's actually easier to have a dedicated Go routine or dedicated thread, and it can be the main thread that is sort of the thread in charge of gathering work that's coming in from a bunch of other threads and actually persisting those results into a shared resource. So that sounds complicated, but let's look at how we can do that with channels. Because if you think about it, there's another problem with this example. So right now, we're going through all of our currencies, we're spinning up a Go routine, and we're fetching currency rates. Great. This is kind of fine because I limited it to be 10 currencies that we're pulling in. But what if we remove that limit and suddenly we're pulling in hundreds or thousands of currencies? With this code, we'd go through all of them and we'd spin up a Go routine to fire off API requests for each currency. What if there's like 100,000, with all the amount of Bitcoin or whatever crypto coming in these days? It might be loads and loads, right? We don't really want to spin up 1,000 threads just to do API calls. What we want instead is we want a worker pool of threads that can basically, whenever they're available, pick up work, and then they can do the work and then return a result, and then they can pick up the next work until there's no more work to be done. And this is a great pattern called a worker pattern or worker pool pattern. It really depends how you look at it. But Go has a great way of doing this by using so-called channels. So let's have a look at what that might look like. So let's implement a function called run currency worker. So this will be a worker that runs, and Copilot's already adding some great ideas. But let's just leave it a little bit. Let's just do it ourselves. So what the run currency worker will do is it will go in and whenever we run it, it will create a threaded worker that will sit there and pick up work to be done, do the work, and return a result. And let's show you how we can do that with channels. So I'll talk you through this channel stuff in just a second. So what am I doing here? So Golang has this concept called channels. Channels are essentially another data structure, but it has some really, really interesting characteristics. So channels is a way of either sending or receiving data into a buffer, essentially, but that buffer has some implementations that make it thread safe in really interesting ways. For example, a thread can write to a channel, which will be a blocking operation. So a thread will sit there and say, I'm trying to write to this channel. Is anyone on the other side ready to read from the channel? And that's what these arrows actually indicate. So you can see, look, the channel type. So we're saying channel. So this one, the currency channel, the arrow on this side indicates that we can read from the channel, and the arrow on the other side means that we can write from the channel. So when we're passing it into a function like this, we're saying, here's a channel, which is a buffer implementation. And the currency channel for this currency worker is one that the currency worker can read from. And the result channel is one that the currency worker can write to. And our channels are also typed. So this channel has a type of currency.currency, right? So currency is, as we see here, our custom struct representing a currency and our currency exchange. So what we're saying here is this worker is going to take an ID so we can identify it, but also 2 pointers to channels, with each channel being a channel that can send or receive currencies, and one of them being for reading and one of them being for writing. So this is a little bit strange, Minnie, but bear with me and I'll show you. It'll make sense when we actually implement it. So let's go ahead. Yeah, we'll take, that's fine, Copilot. That one looks good. So we'll say, okay, we've started the worker. So how does this work? Well, channels are great because they're implemented in a way that allows you to treat them kind of like other data structures that you're used to. So in this case, we can actually iterate through a channel using the for and range keywords that we know from things like lists, slices, maps. And we can actually go in and we can, well, Copilot's kind of done it for us already, but we can walk through it. So we can go in and we can say, this worker will sit here and it will try to read from the currency channel. This is the channel that the worker is trying to read from. Looking at the arrow here. It will go in and it will try to read from the currency channel. Whenever it reads from it, it will print out processing currency. I actually don't want to print that out. We don't need that. Then it will go in and do the work rights. It will fetch currency rates using the code from the currency. It can panic, sure, if it fails. Then it will update the rates and then it will write the resulting currency back to the result channel. So the arrow here is saying, write into the result channel the currency that you just populated. All right? And then another thing we can do is at some point, we probably want to break out of this for loop. And the way channels implement in Go means that they will break out when this channel closes. So you can call close on a channel, and that will cause all these things that are listening, trying to loop through it, to actually break out of their for loop. So in this case, we can say the worker stopped. So now we've implemented our worker So let's go ahead and create some. So imagine or remember what we're trying to do. What we're trying to do is we're trying to avoid having to spin up all these routines all the time for all of our currencies. We just want to have a set pool of workers. So let's create a set pool of workers, right? Let's say, 5 is fine. Let's do this. So first, before we can do that, we need to actually create the channels. So we can say, just like we create maps, this is exactly how we create channels too. So we can use the make function and make a channel of the desired type. And bear in mind, this is just the type. Channels can be anything. They can be channel string, they can be channel bool, whatever you need, right? But also channel of your own type. So in this case, our currency struct. And another thing you can do is make an actually take a parameter, because channels can either be buffered or unbuffered. So unbuffered means it will just try to use as much memory to send as much as you can on the channel. But if you know how much you want to send at any given time on the channel, or how much the maximum is you're ever going to send, and we kind of do that because we know there's only so many currencies in our currency exchange. So we can actually just say the channels need to be no longer than the length of currencies that we have, right? We're never ever going to send more than the total count of currencies that we have. So now we've created the channels, and here we are firing off concurrency workers. So we're creating 5 workers, and they're all going to fire up and listen on these channels. Let's get rid of this, right? We're going to get rid of all this stuff we don't need anymore. We're going to re-implement our for loop as well. So now we fired off GoRoutines for these workers. So how do we actually interact with what's coming back from these workers? Well, the way you can do that in Go, or there's actually multiple ways, but one way I like to do it is we can say, we'll just go inside a for loop, and then we'll actually keep track of how many results we've processed. So we've got result count, right? We'll set it to 0 first. At this stage, we haven't gotten any results back from any of our workers. Then we have a desired finish state. So the desired finish state is exactly this. We want to keep going until we've got results for all of our currencies, right? So then we can say, if we've got all the results, then we can say we've got them all. So let's close the channel, right? So we'll say closing. And we can actually, as I said earlier, we can close a channel, and then we can break out this for loop. So this is kind of our termination sequence. So if this isn't true, we want to do one of two things. We can actually read from the result channel, like so. And this is a kind of special syntax that Go has for this. And then we can store the results like this. So what this means is, let's just walk through this. What this means is select, and we say the case where we're reading from the result channel. Again, look at the arrow, right? So this is us saying we're going to read a value from the result channel. The value is going to be a currency, right? So we'll set that, we'll bind this currency to what's coming on the result channel. And then we'll store that currency in our currencies. That's all we want to do, right? The other thing we'll do is, since we've just processed the result, we'll increment result count, like so. And this is actually the most interesting case. But you might imagine also, we've got multiple threads here that could be blocking on multiple things. So what if we want some kind of timeout as well, right? So another thing we can do is we can actually use this shorthand to say, let's have a timeout on here and say, if it's taking too long for our workers to do stuff, then we're going to get rid of them, right? We're going to time out, and we're going to break and say, tough luck, you took way too long. I was getting impatient. So I've called timeout on you. Let's just go ahead and format this. So again, let's walk through this one more time to make it clear. So we've got a result count that we set to 0. Then we start iterating indefinitely. We go and we say, if the result count is equal to the length of currencies, then we've processed all our results, and it's happy days, right? We close the channel, we break. Closing the channel will cause our workers to break out of their for loop up here. So though they should print out worker stopped. And And if that's not the case, we go into the select statement and we try to read a value from the result channel. So this will block as well. But the select statement is special because this will block, but this one will still execute in the sense that this one will block, but if this one finishes first, this one will trigger. This is why this timeout thing works, that it's set for timer a bit higher. People will say, if it's taken more than 3 seconds, then tough luck, we time out and we break out and we didn't succeed in our operation. All right? But if this one comes in first, we read a currency from the result channel, we store that inside our currency exchange map, and we increment the result count. And then we loop, right? And we go again, and we go again and again until we add the timeout or the result count is equal to all the currencies. Now, if we run this, you might notice that it's probably not going to work because we're missing a fundamental thing. But let's just run and see what happens. First of all, it fails because I have an input that I didn't use. Let's run it. Okay, so the worker started, but you can see we time out. There's no values coming in, right? So timeout again, timeout, it's not happening, right? Nothing's happening here. It's not a good time. So what's going wrong here? Well, there's a couple of things going wrong here. And well, actually, we can actually make it more dramatic like this and say if we return, then we'll exile the whole program. But the crucial thing that we're missing here is we're not sending any work on the currency channel for the workers to pick up. If you remember, the workers sit here trying to read a value from the currency channel, which is their sort of give me some work to do channel. And so we actually need to send all the work to do on that channel. So let's go ahead and do that. So let's iterate through our currencies, like so. And what do we want to do with each currency? All we want to do is you want to send it on the currency channel. So again, look at the arrow, right? So we're just iterating through all of this, and we're sending all these currencies to be processed on the currency channel. This will block, but our workers will start picking it up. And so our main thread will exit out of us. It'll go down here and it will start sort of our channel result gathering loop. So, and meanwhile, all the workers should start picking up this work, doing the work, fetching the result, putting it back on the result channel, and our main thread will pick it up. Our main thread will then bring it all together and hopefully print out the results. So here goes nothing. Let's try that. And there we go. We've now got results coming in again, right? So now things seem to be working. You can see, though, that since we are working concurrently, the printing order is kind of weird, right? So even though standard out, which is what's printing this, is buffered, so at least we don't get characters all mixed up, we do get lines mixed up. So our workers are kind of saying, no, they're actually stopping, obviously, before we print the results, because here we're closing the result channel. But the crucial thing is we are getting our values in, and this worker pool actually doesn't grow even if our currencies grow. So as a final thing, let's try that, right? I've got this thing in here. Let's just say, let's do 100 currencies instead of 10, right? So our workers, we just still only have 5 workers. So it'll probably take longer, right? Let's see if this works. So here, the workers are starting, boom. So it took 1.5 seconds, but we now have a lot more things. And we still only use the same amount of threads, right? We only used 5 extra threads with 5 different workers, but they are doing all this extra work without spinning up all these extra threads. So I hope that was an interesting introduction to concurrent programming in Go, using channels, mutexes, and some of the things you can use. And I hope this is a practical example. As always, I'll leave a link to the GitHub repository for this code in the pinned comment below. And thank you so much for watching. I'll see you in the next one.